Hello everyone. Today we are going to study about the particle nature of radiation. In our previous lecture that we studied about the wave nature of radiation. Let's start. The wave nature of radiation was explained by the Maxwell. By accepting the wave nature, we are able to explain the diffraction and interference phenomena of the light. But we are not able to explain the emission of the radiation from the hot bodies, that is the black body radiation. We are not able to explain ejections of the electron from the metal plate, that is a photoelectric effect. We are not able to explain the line spectra of the atoms. From these three phenomena, I am concentrating on the black body radiation today. Now just give attention. By accepting the wave nature of radiation, we are able to explain diffraction and interference phenomena of light, but we cannot explain emission of radiation from hot bodies, that is black body radiation. Second, ejection of electron by metal plate, that is photoelectric effect. Third, line spectra of atom. Today, we are concentrating on the black body radiation. When a solid is heated, it emits the radiation over the wide range of the frequency. As for example, suppose if we have an iron rod, and if we hit the iron rod, then first it gives the dull red color. As temperature increases on a further heating, it gives the dark red color. The intensity of the red color increases. On a further heating, it's turned into the white, and then after it turns into the blue. From the observation, we can conclude as temperature increases, the frequency of the emitted radiation increases. First, the iron rod is given the dull red color, and the red color lies in a region of lower frequency. At very high temperature, it turns into the blue, and the blue color lies in a region of higher frequency. That means as temperature increases, the frequency of the emitted radiation increases. On the basis of this study, the scientists gave one graph that energy related to the frequency with respect to temperature. You can see on your screen. The graph is actually energy distribution versus wavelength. The energy distribution in a black body cavity at several temperatures. As temperature is rise, the peak shift to the shorter wavelength. But obvious, first time you cannot understand these things. I can just give attention in a graph. At lower temperature, at T1 temperature, you can observe when you heat the substance. See in a graph, when you heat the substance, it increases its wavelength and achieve to the peak value. And then after it shows decrease. Suppose 50 degrees centigrade temperature. At this temperature, first the hot body release the energy, that is radiation. It attain the peak value at T1 temperature. Then after it decreasing its wavelength. Now I heat the substance at more than 50 degree, that is 100 degree. It shows the same deviation. First it shows increase, attain the peak value, and then after shows the decrease. But this peak value is higher than the temperature of T1 because we increase the temperature. Now I am increasing the temperature, that is 150. Then after it shows the same deviation, same graph, but attain the highest value, that is the T3. And if I increase the temperature, supposed to be 1000 degree, then it shows the maximum wavelength at which it shows the maximum peak value. So you observe this thing in a graph. The ideal body which absorbed and emit all the frequency of radiation uniformly is known as black body, and the radiation is known as black body radiation. We can conclude from the graph that black body radiation depends on the temperature. As the temperature increases, the frequency of the emitted radiation increases, but the wavelength decreases. From the graph, you can see that the wavelength is achieved at the peak value, and then after it shows the decrement. Even the temperature increases. This was studied by the Wien, and he derived the one equation, that is T into lambda max equal to constant. He also calculated the value of the constant, that is 2.9 millimeter into Kelvin. With respect to this equation, when we increase the temperature, to maintain the constant value, the wavelength compulsory has to decrease. Clear? Okay, so what we can say that the temperature increases, the wavelength of the emitted radiation decreases. That means the wavelength is inversely proportional to the temperature. This is just for your information, nothing else. Clear? Okay, let's write down all this thing. When solids are heated, they emit the radiation over the wide range of frequency. As for example, an iron rod heated, first it emits the radiation have dull red color. As temperature increases, the intensity of color increases and emits the radiation having bright red color. On further heating, it turns into white, and then after bright blue. I am showing this thing in diagram. This one is the iron rod. On heating, first it gives dull red color. On increasing of temperature, bright red. On increasing of temperature, white, and on increasing of temperature turns into the bright blue. That means the intensity of the color, the frequency of the radiation, it depends on the temperature. From this observation, we can say that the frequency of emitted radiation depends upon temperature. Temperature increases, frequency increases. The red color radiation in lower frequency region, while blue color radiation lies in higher frequency region. Energy distribution, that is rho, versus wavelength, lambda. Suppose at T1 temperature I heat the substance. At temperature T1, the wavelength of this is lambda 1. Now I increase the temperature, that is T2. Same graph, but the peak of the wavelength is more. At T3 temperature, the peak of the wavelength is more, and very high temperature, the lambda T4, the peak value is lambda T4. You can see that this value is lambda 4 and this one is lambda 1. Which one is the higher value? Suppose if I start from origin and this one is supposed to be 1000, then but obvious lambda 1 is higher. That means at lower temperature the wavelength of the radiation is higher. At higher temperature the wavelength of the radiation is lower. So we can say that the T temperature is inversely proportional to wavelength, or wavelength is inversely proportional to temperature. From this observation, the Wien derived the equation T lambda max equal to constant. The value of constant is 2.9 millimeter into Kelvin. Let's define the black body. The ideal body which can absorb and emit all the types of electromagnetic radiation is known as black body and the radiation is known as black body radiation. On the basis of the black body radiation, Max Planck gave the theory of particle nature of radiation. The assumption made by him is, first, the radiant energy is absorbed or emitted discontinuously in form of small discrete packets of energy called quantum or quanta. In case of the wave nature is known as photon. Second, the energy associated with quantum, that is E is equal to h mu, that is equal to hc upon lambda, where the h is a Planck constant. The value of Planck constant is 6.626 into 10 raised to minus 34 joule into second. Mu, frequency of the light, and lambda is the wavelength of the light. Third is the energy emitted or absorbed by body is integral multiple of hv, that is 2hv, 3hv. In general, E is equal to nhv, where n is integer. That means it is not a fraction value.